Okay, so the part 2 no, is actually a problem solving wherein the problem, it has a given beam. Yung beam natin is actually cantilever, no? It is a cantilever beam, fixed. It has a fixed support at A, and then it has a uniformly varying load at B, at point B and C, equal to 16 kilonewton meter, and there's an applied concentrated load acting downward at D equal to 40 kilonewtons, and also we have here a couple, no, counterclockwise in direction 20 kilonewton meter. Okay, so assumption in the problem. Okay, so we have a crack section. So crack na kagad to, no? So using the transformed area method, determine the following. Acting moment, MA, use area method for the shear and moment value. So letter A, you're going to solve for the shear and moment values using area method. And this is actually discussed in your mechanics of deformable bodies and even in theory 1, no? So theory 1. Okay, letter B, draw the shear and moment diagram. Letter C, location of the neutral axis with respect to the bottom of the beam. So naka-specify mabuti dito, no? So kung sa inyo ilolocate yung i-refer yung neutral axis. Okay? So which is at the bottom of the beam. So hindi kung saan-saan, ha? So naka-specify mabuti. So nilagay ko to because kapag wala to, kahit saan, no? Okay? You can get it at the top, no? So it's your choice, no? Kapag hindi ko binigay ito. So since it is specifying the problem, so you need to follow this, no? It should be referred from the bottom. Huh? Okay, letter D. Crack moment of inertia of the beam with respect to the neutral axis. And letter E. Flexural stress of concrete and steel due to the acting moment. Okay, so use N, which is the modular ratio, equal to 9. So you don't need to solve for N, no? So it is already given in the problem. Okay, so this is the given beam, and we have this given beam section. So look at here, no? Siguro napapuzzle yung iba, bakit yung reinforcement nasa taas? Okay? Karamihan yung mga problem natin puro nasa bottom. So try to imagine when you apply load dito sa beam natin. So paano yung curvature niya, no? So yung mga problem natin kasing given do sa lecture, if you notice, once we consider the curvature of the beam, no, with respect to its loading, it is actually concave upward. Pag concave upward yun, yung section ng beam natin above the neutral axis is actually under compression, while the part of the beam that is below the neutral axis is actually under tension. So kapag concave upward yung curvature ng beam natin due to the load. Now, dito sa cantilever, once we apply the load, ang curvature nito is concave downward. Kapag concave downward, the top, no, or we can say above the neutral axis for our beam section is actually under tension, while below the neutral axis is under compression. Kaya ito yung itsura niya, no? So top above the neutral axis will be under tension. So the reinforcement here will resist, no, yung tension doon sa ating beam, while at the bottom is under compression. So we're looking for the location of our neutral axis with respect to this bottom. Okay, so kailangan, no, ganun mo siya kunin, ha? Okay, so but before doing that, we need to consider first A and B, no? So to determine the shear and moment values, so first you need to solve for the reaction and moment at the support, no? So this is now the free body diagram. Okay, so tandaan natin na when you solve for the unknown moment and reaction, you should present a free body diagram. Why? Because you are trying to assume direction. By the way, the direction of our moment here, which is positive, is clockwise, no? So hindi ko na nilagay, but it's actually clockwise. Okay, so you need to present a free body diagram because I cannot check your equation without a free body diagram. How do I know kung tama yung mga direction mo kung wala kang free body diagram, no? Okay? Kaya tandaan niyo yun, no? Without a free body diagram, you cannot do this. Okay? So ngayon, yung free body diagram natin, RA is assume upward, vertical. MA is counterclockwise in direction. So here, I'm going to solve first for the moment. Okay, the external moment, A. So we have, so we're going to use summation of moment equal to 0, clockwise direction positive. Okay, so I'm going to put here, sigurado tayo. Clockwise direction positive. So yun yung magiging ano natin, no? Magiging direction natin. Assume direction for our moment, no? Moment equation. Okay, so the uniformly varying load now, when we convert this into a concentrated load, all you need is get the area, and that is equal to 1/2 16 multiplied by 1.5, and this load will produce a clockwise moment. Clockwise moment yan with respect to A, and its moment arm is what? 2/3 of its length, no? Yung length ng load, which is 1.5, ayan, plus 0.75. So that will be the moment produced by this load. Now for the couple, 20 kilonewton meter, this is already a moment. So dahil moment yan, all you need is look at the direction. Ang direction niya counterclockwise, kaya negative. Okay? Now for the 40 kilonewton load, okay, it will produce a clockwise moment. So that is why it is positive. Okay? And then your RA will be eliminated because our moment center is at A. Only moment A now will be considered, and it is counterclockwise in direction, so it will be negative. And this one is equal to 0. So this is how we write, no, our moment equation. Then isolating MA, MA is 121 kilonewton meter. And this is what? Positive. So yung result is positive, so therefore tama yung direction mo dito, no? Counterclockwise. Okay? And then for RA, we're going to use the second equilibrium equation, which is applicable, no, dito sa ating given beam. We have summation of forces about y equal to 0. So again, Ang assumption dito, ang assume direction natin is upward force positive, no? Yun yung ano natin, no? So upward force positive. So then, no, RA is upward, so it will be positive. 40 kilonewton is downward, that is why it is negative. And the equivalent concentrated load of this uniformly varying load will be acting downward. So that is why also it is negative. So the couple will not be included because this is a moment, not a force, no? So we equate it to 0. So isolating RA is 52 kilonewtons and it is positive. So therefore, correct yung direction natin. So our RA is upward. Okay, next, we're going to consider the shear values, no? So in mechanics of deformable bodies, this is actually the method that I presented, no, to my class, wherein if you have a load at a particular point, you're going to consider the positive and the negative and the positive, no? Not really, but it's just a designation wherein you have to have an initial shear, no? Wherein you don't need to consider first the concentrated load. So at point A, there's a concentrated load which is RA, no? So you consider first the loadings, no? The loadings in the beam, no? Without considering the concentrated. So at point A, there are no loads in the beam. So therefore, your shear will be equal to 0. Now, the second consideration at point A, no, in determining your shear, okay, so you're going to add your first shear, V1A. Actually, in mechanics of deformable bodies, ang symbol ko dito positive. But using MathCAD, I cannot put positive here, no? So kinu-question ng MathCAD 'yon as my designations. So I just simply make use of V1 and V2. So sa mechanical deformable kasi I put a symbol or a designation here as V negative A and V positive A, no? So I just put here 1 and 2, no? Okay. So you're going to add your initial shear, then you add your concentrated load. And our concentrated load here is acting upward, and the assumption that I have presented, no, sa mechanics of deformable bodies is that upward force are considered positive in terms of the sign convention. Kaya dito yung RA mo positive. So therefore, your shear at A will be 52. Kaya dito makikita mo, you will start at 0, which is true, no? When you draw a shear diagram, you always start at 0. Then you proceed to the next shear. No? So ito yon, no? You start at 0, then you have your 52. So makikita natin mamaya yan doon sa diagram natin. And then, the next point now will be B, no? So, yung equation, yung area method, kailangan kunin mo yung area ng load dito sa beam between A and B. Kaso wala. Kaya 0 yung area mo dito, no? So, ang equation mo will be B sub B equal to yung previous shear mo plus yung 0 area ng load. Kaya yung shear mo 52 ulit. So, ibig sabihin from A to B, your shear is 52. No? So, constant yan. And then at point C, no, you have this uniform load. this uniformly varying. So makukuha natin yung area nito, no? So ito ngayon B sub C. So we're going to add the initial plus the area nung load. And since that load is acting downward, kaya negative siya, no? Ang result ay 40 kilonewtons. And then at point D, again there's a concentrated load here. So we have an initial shear considering the area of the load between C and D. So wag mo munang i-consider yung concentrated. Kaso walang load dito, kaya zero yung area between C and D. Kaya yung formula natin, B1D equal to VC plus 0. Dahil walang area yung walang load between C and D. So again, our shear is 40. And then, the next step is you solve now for the shear at D, this time considering the concentrated load. So you have B1D plus the 40 kilonewton load. So since it is acting downward, it will be negative. So the result is 0. So look at here, no? This is actually the shear, no? From 0, then for a certain value, then magko-close hanggang mag-close yung ating diagram. So when we look at now our shear diagram, ito yung diagram natin, no? So it will start at 0, 52. Then since walang load dito, when you connect now these two, it will be using a straight line, no? A horizontal line, no? Then from B to C, you have here a uniformly varying load. So 0 intensity, maximum intensity. So your curve will be concave downward. Concave downward yan, no? Hindi concave upward, okay? And then at C, you have 40. And since there are no loadings here, when you connect your shear at D, it will be using horizontal line. So this is, and then it will close, no? Because at your V2D is 0. Kaya mag-close. So ito yung ating shear diagram. Okay? Now for the moment values, so you're going to use this diagram, no? So at point A, when you look at your beam, at point A you have an external moment, MA. And this is counterclockwise in direction, so that is why it is negative. So negative 121 kilonewton meter, no? And then for your B, sa B meron kang couple. Dito magkakaroon ka ng dalawang moment. Okay, first you're going to consider the area of your shear diagram, no? Pagkatapos, yung pangalawang moment mo, i-consider mo na yung couple, no? Yung couple na i-consider mo. Kaya ito yung diagram natin, no? M1B, MA yung previous plus yung area nung moment ng shear diagram mo, which is a rectangle. So the shear 52 multiplied by 0.75, no? So ito yon. Ito mismo yung rectangle na yon. And this is equal to negative 82. And then at M2B, so the second moment at point B, this time you're going to consider the couple. And the result is negative 102. Okay? And then at C, no? You're going to consider now the area of your shear diagram. Dahil wala ka namang couple dito, kaya MC lang, no? So ano yung area natin dito? Yung rectangle at saka yung 2/3. 2/3 of the difference between 52 and 40. Okay? So kaya nandun, no? BC 1.5, which is 40. And then V sub B minus B sub C. So that is 52 minus 40. 2/3 of 1.5 is negative 30. Okay? And then the last one, yung area mo dito, again rectangle, so 40 multiplied by 0.75, ayun. So 0. So ang MD mo, it's like checking ito, ano? Bakit? Kasi wala kang moment dito. Kaya automatic 0 to, kaya tama, no? So 0. So when you draw now your moment diagram, so first you have your MA, negative 1 to 1, and then you have here what? A horizontal line. So therefore, when you connect negative 121 and negative 82, you're going to use a straight line. Dahil yung intensity mo dito, constant. So you have a constant slope. Okay? And your shear is positive. So therefore, yung slope mo upward. Kaya positive din. So those are the relationship, no? Between the shear and the slope of your moment diagram. Okay? And then after that, your moment at B is negative 102. So connect mo lang yan, no? And then pagdating ngayon dito sa ating C, our computed moment is negative 30. So how do we connect it from negative 102? So look at your diagram in your shear, no? The intensity is maximum here and it is minimum here. Okay, mas maliit dito doon. So therefore, kapag pinlat mo yung moment diagram mo between B and C, it should be what? It should be concave downward. No, it should be concave downward. The slope here is maximum while the slope there is minimum. Okay? So gano'n, no? Kailangan concave upward yan. Then at CD, again, you have a constant intensity. So all you need is connect negative 30 and 0 by straight line. Again, the slope is upward because the shear is positive. So you have a positive slope because your intensity or your shear is positive. Okay, so yun yung ating moment diagram, no? So these are A and B requirement in your problem, no? So yun, no? So kung titignan natin yung problem natin, yan, no? A and B. So the next requirement is location of the neutral axis with respect to the bottom of the beam, then crack moment of inertia. So without the location of your neutral axis, hindi mo masosolve to. Similarly, ganun din sa flexure. Hindi mo rin makukuha yung tamang flexure without knowing kung asan yung neutral axis mo. Kaya itong tatlong to, no? Related to one another with respect to the location of the neutral axis. Okay. Let's move on now to the location of the neutral axis. So this is now the transformed area. Huh? Okay, so you have here an assumed location of your neutral axis. And this is now the concrete under compression. And this is now the equivalent transformed area of the steel. So it should be located at what? At the centroid of the group of bar, no? So kailangan, no, nandun siya. Okay, so ano yung ginawa natin dito? To solve for the area of this compression, no? Compression part ng ating beam. Okay, what we did here is we get the slope of this. Yung slope niya is based from the slope here, which is what? 250, it's actually 600 is to 250, no? Vertical to horizontal, no? So 600 is to 250. Now, we express it to its lowest term. Ayun. 12 is to 5. Yung slope. Okay? So 12 is to 5. Now, to get the area of this, no? To get the area, ito yung pinaka-solution natin. So I'm going to take the difference, no? Take the difference between rectangle and triangle, no? Okay, asan yung rectangle? Ito, itong buong rectangle na to. Then I will subtract these two triangles. So that will be my area, no? Area for the concrete. Okay. So and then what I need now is the distance here. So the depth here is KD. Okay. So what I need is X. So X can be solved in terms of KD by ratio and proportion. So ito siya, no? So by ratio and proportion. That will be the equivalent value of our X. Now, so what I did here now sa area of the steel, I solve AS1, AS2, and then I sum up it. That will be your AS. And then, so after knowing AS, for the area, no, area of okay, so for the area of the concrete, ito, no, ito yung pinaka-formula natin. And then for the location, of location of the centroid of the rectangle and the triangle, we have KD over 2, while yung ating triangle is 2/3 KD, no? 2/3 KD. Okay. Okay, so the equivalent transformed area of the steel, so we have this one. And then solving for the effective cover. So this is the location of the centroid. Location of the centroid of the rebar, no? Of the rebar. It is referred to the apex. Do sa apex, no? Yun ang pinaka-reference natin. So minoment natin yung area with respect to the apex. So masosolve natin yung T prime. So ito ngayon yung T prime. Okay? And it is equal to 200, no? And then solving for the effective depth, it is equal to 400. Okay, total area. Okay, so we have concrete and the transformed area of the steel. So we have this resulting equation. Okay? Now, the determination of the location, no? Location of the neutral axis. We're going to take a moment of the area about the bottom of the beam. Okay, so area total multiplied by KD, multiplied by the area of the rectangle, multiplied by the location or the distance of the centroid of the rectangle, designated as Y rectangle, no? And then the area of the triangle, yung dalawang triangle kaya naka-multiply ng 2. And then yung distance nung centroid nung triangle ay designated as Y triangle. And then for the equivalent transformed area of the steel, multiplied by D. No, D is the effective depth of the section. So ngayon, substitute natin yung mga known values. Area total, no, substitute here. Yung Y rectangle natin is 1/2 KD. Yung Y triangle natin ay 2/3 KD. And then the area, it will be 5/12 KD square, no? Bakit 5/12 na lang? Kasi yung 2 at saka doon canceled out. Then yung area nung transformed area of the steel, multiply by D. So simplify this, you will have this resulting equation. So kapag ang sagot mo, no, meron ka kagad sagot dito, I will not accept that because you need to show kung paano mo nakuha yan, no? Okay, and there is a method kapag ang equation mo cubic. And this is taught in your numerical methods. Kaya nga tinuturo ang mga method na yon, no, para magamit nyo. Remember, no? Kapag dependent ka sa calculator mo, darating ang araw, no, wala yan. Hindi mo magagamit yan pagdating ng board exam. Kaya kailangan alam mo kung anong gagamitin mo, no? So the best method, no, to solve the KD is by the use of the Newton-Raphson method. Okay? So ang gagawin mo dito, equate mo yung equation mo to as a function, no? So ang ginawa ko dito, I equate KD to x, no? So I designate this equation as f of x, and then you get the first derivative. Ito yung first derivative niya, no? F prime x, f prime of x to, no? And then you're going to assume an initial value. Ito yung initial value mo, and then use this formula, no? You get the first result of the iteration using what? X minus the ratio of f of x to the f of prime x. So substitute mo ngayon yung value nitong f of x and f prime x dito, and the result is 125.2060. Then you use again this one, no? You solve again, no? At ang result ay 125.141. Okay, again you use again this one. So that will be now for the third iteration. It shows here that at the third iteration, yung value mo hindi na nagbago. Pag hindi na nagbabago yan, that's already the value of your KD, no? So therefore, our KD is 125.14. Okay? So this is the computation, no? On how to get your KD if you have a cubic equation. So one of the method is Newton-Raphson method. Ito yung pinaka madaling tandaan, no? Yung iba kasing method, medyo hindi ako familiar, but there are a number of methods, no? Like yung bisection method, and I think meron pang iba, no? So tinuturo yan sa numerical. So dito nyo makikita yung application, no? And even in hydraulics, no? Okay, magagamit nyo rin to dahil meron ka ring mga equation doon, may mga topic doon na wherein you're going to solve for a certain value. Ang mapoproduce mo is actually a cubic equation, no? Okay, so after knowing your KD, you may solve now ICR, no? So this is the computation. Yung rectangle mo, merong direct formula which is BH cube over 3. And similarly, ganun din to sa triangle. Yung triangle, ganun din, no? Yung base multiply by the altitude cube over 12. So, diretso rin yun, no? And then, your equivalent steel, no? Your transformed area of the steel. So, dun mo lang gagamitin yung transfer formula, no? So, substituting now, the result is, we have this, no? So, this is your ICR. So, once you have your ICR, you may solve now the stresses, no? The stresses in the steel, okay? And the stresses in the concrete. So, this for the concrete, 11.55 megapascal. While in the steel, you have 228.34 megapascal. Okay? So that is the solution of your quiz, no? Yesterday, no? Okay? So yung mga solution na nakita ko, I think meron na akong mga questions dahil meron akong nakita hindi ganito yung beam, no? Okay? Na nakita ko. Okay? So I think the reason why I gave this one, yun ang pinakadahilan, no? Para makita ko kung hanggang saan ba yung pagkakaintindi nyo doon sa pinag-uusapan natin. Yung iba hindi ma-imagine na nakabaliktad. Siguro nagtataka, meron ba talagang ganyan? Meron, no? Ayan, Nakita nyo na, no? Na yung bakal mo nasa taas, yung baba wala. Okay? So, yun yung yung dinidesign mo nasa taas because yung bending, no? Because of the bending. Okay? So, I think that is the solution of your quiz. Okay? So, so far ang nakita ko ang ano nga, they reverse this automatic, mali ka na, no? Because what I'm asking is at the bottom. Okay? Ang ginawa nyo at the top. Okay? So kaya automatic mali na, no? Okay? So yun yung ano natin, ha? Yun yung ano natin. I hope nakatulong ito, no? Para mas maintindihan nyo yung pinag-uusapan natin, no? You need to know first asan ba yung compression, asan ba yung tension. Very important yan. Pagdating natin ng design, no, doon yung makikita, no, na bakit meron bang ganito, no, sa mga beam na naka-concave upward. Na sa tingin nyo concave upward, no? Actually, in actual, specifically for building, no? Yung mga beam natin doon are actually what? S2 bending. Actually, tatlong bending ang mga beams, no? Una, naka-bend yan concave downward at the left support, then concave upward at the midspan, and then concave downward uli at the left support. Because yung beam natin sa mga building walang simply supported. Wala, no? They are all what? Puro fix. Okay, puro fix yan because of the method of construction. Tignan nyo, ano yung connection ng mga reinforced concrete beam? They are all what? Monolithic pagdating sa joint. Pag monolithic ka natin, isang buhusan lang yan, no? Kaya yung behavior ng beam mo, it's not simply supported, but rather what? Fixed on both end, no? Okay? They are fixed on both end. Kaya meron kang moment doon. Meron kang negative moment at meron kang positive moment at the midspan. Okay? So, pag tinignan mo yun, ang bending nun, tatlo. Okay? Tatlo ang bending niya. No? Sa support, kapag meron siyang negative moment, ibig sabihin, ang tension niya nasa taas. Okay? Kapag positive ang moment, ang tension niya nasa baba. Kaya nga yung istaad, no? Yung istaad, ang ginawa ng istaad, binaliktad niya yon. Kapag nag-draw ng moment diagram ang istaad, kung saan yung bakal, doon yung moment. Like for example, at the midspan, ang bakal mo nasa baba, no? Dahil positive ang moment na alam natin. Ang istaad, ang ginawa niya sa baba. Nasa baba yung moment para coincide dun sa position ng bakal. Ngayon, doon sa support, yung moment niya nasa taas. Dahil yung kanyang reinforcement nasa taas. So, ganun ang istaad, no? Sa programming niya. Kung saan yung moment, doon yung bakal na para sa beam. Okay? So, I think that is for the solution of the quiz yesterday. Okay, so I'm going to check your paper this weekend. So para may balik na sa inyo, no? Okay, so let's proceed now to our next lesson. So our next lesson, we will proceed to the strength design method, no? So mapapansin nyo, wala tayong design of beam using WSD because the code doesn't allow anymore, no? Yung design ng specifically mga buildings, no? Using the WSD. Okay? So the code specified that we need to use the strength design method. Okay? Kaya yung analysis and design is involved, no, pagdating dito sa ating strength design method. Okay? Nakikita na ba yung ating presentation?
Yes, sir.
Okay, so let us proceed now. So I'm using the PDF format of our lecture, no? Hindi na yung PowerPoint, no? Para at least ma-monitor ko kung connected ako. No, itong week na to, meron akong mga experience, no, na nadi-disconnect kasi, no? And if I'm using a PowerPoint, hindi ko ma-monitor, no? Hindi ko ma-monitor kung connected pa ako. Kaya dito pag kapag naka-PDF, no? Nandito yung taskbar ko, no? So nakikita yung connected pa rin. Okay, so willing bang i-record yung ating lecture? Yung ating meeting?
Yes, sir.
Okay, so sige.
Yes, sir.
I'm asking this kasi tandaan natin kapag nag-record tayo, yes, ayan. Mukhang yun din ang concern siguro ni ni Mr. Pagarigan, no? Okay. Okay, so okay, so let us look at this introductory part of our lesson, which is all about strength design, no? We have here two figures, no? Showing here the stress strain diagram for steel and for concrete, no? So mention here that structural concrete and reinforcing steel both behave inelastically as ultimate strength is approached. Okay? So kapag WSD tayo, doon yung elastic, no? So pagdating ng ultimate strength, our material is no longer elastic. So they behave inelastic. Okay? So tandaan natin mabuti 'yan. I hope you still recall yung yung kapag yung material natin elastic and inelastic. So very important 'yan, no? In theories dealing with ultimate strength of reinforced concrete, the inelastic behavior of both material must be considered. Okay? So ito yung ating stress strain diagram for steel. When we test a steel, pag tinest natin yan, meron niyang linear part. Ito, no? So yung linear part nung ating diagram, yun yung elastic behavior. Yun yung stage kung saan elastic yung behavior ng material natin. Once it reach the yield point o yung yield distress, our material is no longer elastic, no? So kaya nga dito makikita nyo, we are already using FY sa design, no? Sa analysis, we are already using the yield strength of the material. So look at here. Yung steel natin, even though it has already a permanent setting, once it reach the yield point or the yield stress, it will continue the diagram or the graph will continue to rise, no? Because it can still resist load, kaya tataas pa rin yan until it reach the ultimate. Ito yung pinaka-ultimate, no? Pinaka-ultimate, yun yung maximum stress ng ating material. And then once it reach the ultimate in theory, no? Pag naabot na niyo yung maximum, pag nilagyan mo pa ng additional load, its capacity now will go down. So yung stress niya bababa na yan theoretically, no? Until mag-fail yung material natin, kaya putol dito, no? Okay? So yun yung ating stress strain diagram for for our material. But in design, sa design and analysis, hindi natin ginagamit yung ultimate strength o yung ultimate stress ng material. Anong ginagamit natin is the yield. Kaya mapapasin nyo dito itong dash line, it represent now here, no? It represent the stress strain diagram of our steel when we analyze or design, no, a reinforced concrete member. So ibig sabihin, throughout, no, at any given strain, our Fy, our stress is always equal to the yield. Kaya ito yon, no? So equal to the yield strength. Okay, so we never make use of the ultimate, no? Okay, so pero ano yung pangalan ng method natin? Ultimate strength design. Kaya inalis na yung ultimate, no? Kasi kapag nakausap mo yung isang kliyente or someone read this, no? You are considering the ultimate, no? So you are considering yung pinaka sagad, no? Yung pinaka failure ng material, okay? Okay? So instead of using that, we make use of Fy, okay? Kaya kapag nag-analyze ka, nag-design ka, when you check for the stress in your reinforcement, you always limit it to Fy. No? It doesn't matter kung sa computation umabot siya ng more than Fy. So you always consider it as Fy, okay? Equal to Fy, okay? So later on, pagdating natin sa mga computation, makikita nyo yan, no? Okay? Okay, so that is about the stress strain for our reinforcement. Now, for our concrete, eto, no? So yung elastic stage ng concrete natin is actually when your section is uncracked and cracked. That is why our allowable stress for our concrete is 0.45 F prime C. Okay. Now in strength design, we consider FC prime, and that is what our material, our concrete behave now inelastic. So saan natin nakukuha itong F prime C? Okay? When we test, di ba? Pag nagte-test tayo ng concrete sample, no, yung concrete cylinder, okay? So yun yung pinaka F prime C natin, okay? So nakukuha natin yung kapag nag-crack na yung ating concrete, di ba? Pag nagte-test ka habang hindi nagka-crack yan, patuloy na tumataas yung stress niya, no? Because your concrete resists load. But when your concrete cracks, kahit na anong dagdag mong load, hindi natataas yung reading mo, no? I hope you experience that, no, in your testing. Ha? So kahit na anong dagdag mo, no, ang ginagawa mo na lang nun, kinakrush mo na lang yung konkreto mo, no? Winawasak mo na lang yung cylinder sample mo. Pero yung load mo hindi natataas kahit na anong gawin mo, no? Because once the concrete cracks, it will no longer resist load, okay? So yung tandaan natin. So ito, no? So we are using F prime C, okay? So our material behave inelastic, no? For you to know, no? Ano ba yung binabanggit dito sa introduction natin? Okay, so that is for the first slide. For our second slide, no? Sabi dito, the term ultimate is used frequently in reference to the strength design method. However, it should be realized that the nominal strength, look at that, no? The nominal strength computed under the provision of the code may not necessarily be the actual ultimate value. So when we compute for the strength of our beam, we are actually solving for the nominal, and the computation of the nominal strength is based from the code. Kaya dito, no, kung i-compare natin sa test ng mga material natin, hindi ito, no, hindi ito yung tinatawag nating actual ultimate value. Okay? So within the design assumption permitted, certain properties of the materials are neglected and other conservative limits are established for practical design. So yung content ng mga formulas na ginagamit natin, meron tayong mga assumptions doon, no? Para yung result natin conservative. Ano yung conservative? Para nasa safe side tayo, no? So this contribute to a possible lower ultimate strength, no? So look at that, okay? So mas mababa, no? Than the obtained by test. So for you to realize what is meant by strength design, no? The computed nominal strength should be considered a code-defined strength only, no? So nasa kung ano yung requirement ng code, yun ang susundan natin. According to the term ultimate, it is not used when defining the computed strength of the member. The term nominal strength is used instead. So when we're talking of the strength of a reinforced concrete member, we are referring to the nominal, okay? To the nominal strength, and the nominal is a code-based. Code-based yan, ha? So hindi yan comparable to sa ating test. And it is always lower than, no? Lower than, no? What is obtained from test, okay? So for you to realize, no? What is a strength design. Okay, so in the computation of the nominal strength, okay, we have this following assumption. Number one, strain in the reinforcement and concrete shall be assumed directly proportional to the distance from the neutral axis. So, linearly varying yung ating mga diagram, no? Specifically our strain diagram. Similarly, no, ganun din dun sa ating sorry, it's more on the strain. I'm sorry. It's more on the strain. So linear yung ating relationship, no? So kaya dito makikita nyo, directly proportional sila, no? So using this, we may able to establish what we call yung compatibility, yung strain compatibility equation, no? Nung ating concrete at nung ating steel. Okay? So we're talking of the compatibility equation, no? Okay, so for the usable strain in concrete, the code permit us to use 0.003. So this is the maximum usable. Okay, so why is it they are using this? No, look at here. Based from test, it shows here that the lowest strain for concrete is actually at 0.003, no? So look at this diagram, okay? Okay, for column and for beam. So this is according to test, no? So hindi ito hinula, no? So approximately, no? So ito yung kinuha, no? Ng kinonsider ng ACI code, no? Ng code, okay? Kasi pag ACI ka natin, yun din ang inadapt kasi ng NSCP. Okay, so that is about the usable strain in the concrete, no? So ito yon, yun yung maximum, no? Maximum usable strain in the concrete. So yan. Okay, so the third design assumption. So as I have mentioned a while ago, no? Ito, no? Sabi dito, stress in the reinforcement Fs below the yield strength Fy shall be taken as Es times the steel strain epsilon s. For strain greater than Fy over Es, no? So I hope you still recall yung definition ng strain. Okay, yung definition ng strain, di ba? Strain ay yung Hooke's law, no? Para mas madali nating tandaan. When we define Hooke's law, ano ba yung Hooke's law? Hooke's law is stress is directly proportional to strain, and that is stress equal to E multiplied by strain equal to E multiplied by stress is equal to E multiplied by strain. So that is Hooke's law, no? So ngayon, when we solve for the strain, it is equal to stress over E. E is known as the modulus of elasticity. Ito yon, no? Sabi niya for strain greater than Fy over Es. So, Fy over Es, ito yung yield strain ng reinforcement natin. Pag meron ka ng Fy, kaya natin, you're talking of the yield, no? So, kapag yung kinonsider natin yung yield strain sa steel, that is already the maximum yield strain in our steel. Kasi tandaan natin, sabi ko nga sa inyo kanina, di ba? Kapag kinonsider natin yung stress sa steel, it's only Fy, no? So hindi ka lalagpas doon. Nakalimit sa Fy. So sabi dito, stress reinforcement shall be considered independent of strain and equal to Fy. Okay? So ibig sabihin, yung kapag yung strain mo is greater than the yield strain, automatic yung stress mo dun sa steel mo equal to Fy. So automatic yon, no? Kaya ito yung ating equation, no? Kapag yung strain in the steel is equal or less than this is less than, no? So paki-correct lang to. If your strain in the steel is less than the yield strain, no, yung epsilon y is known as the yield strain, the determination of your stress in the steel is equal to Es multiplied by epsilon s. Yun yung magiging equation mo, no? So mamaya makikita natin paano natin i-compute itong epsilon s, no? So babalikan natin yung diagram kanina. Itong diagram dito, no? Gagamitin natin to, yung compatibility strain, no? Ng mga material natin. So ito, no? So then, no? It follows now that when we solve for the tensile force, yung ASFS is known as the tensile force. Yung tensile force do sa ating reinforcement. Therefore, it will be equal to what? AS and Fs now will be equal to Es epsilon s. So this is how we solve our tensile force, and also how do we equate our Fs, that is the stress in the steel, if the strain in the steel is less than the yield strain. Now when your strain in the steel is equal or greater than the yield strain, your Fs will be equal to Fy, because your epsilon y is equal to what? Fy over Es. Yun ang magiging value niya. Kaya Fs is equal to Fy. Kaya makikita yun yung diagram kanina, no? Okay, so flat na to. Because kahit na anong value nung Es mo, as long as it is greater than or equal to epsilon y, your Fy will be constant. Okay, your Fs will be equal to Fy. What I mean, no? So, yun yung ibig sabihin ng diagram kanina. So, therefore, when you solve for the tensile tensile force in your reinforcement, it will be equal to ASFy. So, tandaan nating mabuti ito, no? Pagdating sa analysis and design, Okay, we will consider this, no? Itong mga condition na to. Okay, so design assumption number 4. Okay, so pagdating natin ngayon dun sa concrete force, no? Okay, yung compressive force natin. Yung kanina, we're talking here of the tensile force in the reinforcement. How about our compressive force in the concrete, which is under compression? So how do we determine that, no? So ito ngayon. Sabi dito, tensile strength of concrete shall be neglected. So wala na, no? Dahil nag-crack na yon. Flexural calculation, no? In axial and flexural calculation of reinforced concrete. So neglected na yung tensile. Only concrete, only in compression sa concrete ang i-consider natin. So that is number 4 assumption. We will not consider the tensile strength in concrete. So it will be 0, no? Then we move on to design assumption number 5. So for the determination of the concrete force, no, or the compressive force. Okay. So sabi dito, relationship between concrete compressive stress distribution and concrete strain shall be assumed to be rectangular, trapezoidal, parabolic, or any other shape that results in prediction of strength in substantial agreement with the result of the comprehensive test. So, yung code natin, ina-allow niya, no, allowed niya kung ano yung magiging possible shape, no, ng compressive stress mo, no? So, but remember, as I have presented a while ago, ito, no? So, balikan natin. Ito yung diagram nung stress strain diagram natin, no? Ito yung pinaka-diagram nung concrete kapag tinest mo yan, no? So it's actually parabolic in shape, okay? Kaya lang ang hirap i-predict yan, no? Dahil nagbabari yan, no, in actual. For every material you test, nagbabari yan, okay? But they have a similarity, no, kapag ano yan, it's actually parabolic in shape. So but the code allowed us, no, kung ano man yung gusto mong maging shape ng compressive compressive stress do sa concrete. Kaya lang, you see to it that it is what? Sabi niya dito yung result nung magiging diagram, compressive stress diagram mo, must be in substantial agreement with the result of comprehensive test. So dapat yun ang masatisfy mo, no? So ito yung mga different recommended na diagram, no? Diagram, no, compressive diagram ng concrete, okay? We have the 1936, 1938, and 1949, no? Na mga diagram, no? Okay? Yun yung mga according to ano yan, no? Yan yung mga recommendation noon, no, ng mga engineers, no? Mga researchers, no? Yan yung mga recommended shape ng compressive stress ng concrete, wherein they base it from the test, no? Sa test yan, okay? Now, we have here also, no, figure or compressive stress diagram. This is given by Hognestad and Todeschini, no? Todeschini, okay? Yung kay Hognestad, no? We call it as the modified Hognestad stress strain diagram. Sabi dito, a common representation of the stress strain diagram or stress strain curve for concrete with strength up to about 6,000 psi. Okay, so this consists of a second degree parabola with apex at a strain of 1.8 F double prime C over EC, where F double prime C is equal to 0.9 F prime C. Okay, followed by a downward sloping line terminating at a stress of 0.85 FC double prime. So ito yon, no? Second degree parabola at this point, yung pinaka-apex, then straight line until no, it reached the strain at 0.0038. Okay? So ito yung modified Hognestad. Okay? The value here is actually F prime, F double prime C. Yun yung pinaka-apex niya. And that FC double prime is equal to 0.9 F prime C. No? So yun yung pinaka-diagram ni Hognestad. No? Now, si Todeschini, throughout, it is a second order parabola. No? Throughout yan. And look at yung work ni Todeschini, no? Yung pinaka maximum stress dito sa diagram na to is similar to the modified Hognestad, which is also equal to 0.9 F prime C. Okay? And also the value of the strain, yung value ng strain kung saan nag-occur yung ating maximum stress. Okay? So yung kay mga Hognestad, it is equal to 1.8 F C double prime over EC. While yung kay Todeschini is 1.71 F prime C. So kaya kung i-convert natin sa F prime C, yung kay Hognestad, we simply multiply it by 0.9 F prime C, no? So 0.9. So yung 1.8 natin, i-multiply natin ng 0.9. Pag minultiply natin ng 0.9 yan, lumilitaw it's 1.62 F prime C, no? So mas no? Mas maliit. Mas maliit yung strain value nung kay Hognestad compare it to kay Todeschini kasi nasa 1.71 yung kay Todeschini, no? Yung kay nasa 1.62, no? It will make use of yung 0.9 F prime C, no? Replacing FC double prime here. Okay? So yun yung ating mga shape, no? Shape ng ating concrete, no? Stress strain diagram. Now, so yun yung design assumption number 5, no? So that is permitted by the code. But then again, kapag kasi parabolang ganun, ang hirap, no? I-treat, no? Ang hirap i-treat niyan dahil parabolic at for every concrete specimen, no? Kapag tinest mo yan, nagbabari kasi, no? Kaya ang hirap i-predict niya. Kaya ngayon, ang ginawa, merong isang study na wherein this parabolic shape ng ating compressive stress in concrete, no? Inequate yan into a what? Into an equivalent rectangular concrete stress distribution. So ginawang rectangle. And we call this as the work of what? The work of Whitney, no? So nakalimutan ko na lang yung first name ni Whitney, no? We call this now as the Whitney rectangular concrete block, no? Or compressive block, no? So si Whitney, no, ang ginawa niya, yung concrete stress, it is maximum at 0.85 F prime C. No, maximum yan at 0.85. Ito yung rectangular equivalent. Whereas ito naman, ito yung actual shape ng stress diagram, no? It is actually parabolic. Okay? And then, para ma-satisfy, no? Ma-satisfy ni Whitney, no? Yung test, no? Kasi kinumpare niya to sa test, no? Nang sinuggest niya yung rectangular. So ang ginawa niya ngayon, meron siyang isa pang adjustment. Aside from the maximum stress, which is 0.85 F prime C, yung kina Ognestad at saka kay Todeschini 0.9 eh. 0.9 yung maximum nila, no? Kaya lang parabolic nga lang yung kanila, no? Eh siya ang ginawa niya rectangular. So ginawa niya ngayon yung maximum stress is 0.85 F prime C. So ang ginawa niya ngayon to satisfy yung test, no? Ang ginawa niya ngayon yung hindi niya ginamit yung neutral axis, no? Hindi niya sinagad itong compressive stress up to the neutral axis. Unlike if it is a what? If you are considering the parabolic. Ang parabolic kasi hanggang neutral axis yan, no? Magsi-zero yan up to the neutral axis. Actually, itong zero stress, ito yung umpisa, no? Pag tinignan nyo, ito yon. Pag tinignan nyo to, ito yon, no? So dito nag-i-start papunta doon. Di ba? So pasinin nyo, ito yon. Oh. So pag kinumpare nyo dito, ayon. Pag ganyan siya, no? So zero at the neutral axis, then tumataas yan, then bababa doon. Okay, so ito yung diagram natin doon sa compressive stress, no? Okay, now, ang ginawa niya ngayon, in-adjust niya, no? By the way, paki-correct itong figure, no? Itong depth nitong ating rectangular must be hanggang dito. No, hindi ito, no? Hindi kasali ito, ha? So hindi ko na correct ito, no? So hanggang dito lang, ha? With the depth A, no? So yung ating rectangular compressive block, ang kanyang pinaka-depth ay equal to A, designated as A, wherein A is equal to beta 1C. Okay, so merong factor na minultiply dito sa location ng neutral axis. Kasi ang neutral axis natin up to the extreme compressive fiber is C. So ngayon, para masatisfy niya yung test, no? Para mag-coincide. Kagaya ng binabanggit dito, di ba? Sinasabi dito, kailangan yung prediction mo do sa result, no? Must be in agreement with the comprehensive test. So ang ginawa ngayon ni Whitney, yan, no? Yung depth nitong rectangular block ay equal to A. And A is computed using this formula, beta 1C, wherein C is the depth of the neutral axis. Okay? So the computation now of the beta 1, meron tayong sinusundan. So wag na nating intindihin yung nakasulat dito. Mas madali kung titingnan natin dito. Ayan. Ito yung condition, no, para makuha natin yung depth ng rectangular compressive block, no? So as mentioned here, ito ang tawag dun sa ating equivalent rectangular block ay Whitney stress block. Okay? So this is proposed by Whitney, no? Okay? So I forgot the name, no, of Whitney, no? Lalaki to, baka ma-imagine nyo si Whitney Houston, no? Okay? Okay. a uniform compressive stress of 0.85 as I have mentioned, no? Ito ngayon yung computation natin ng beta 1. Okay. So we are what? Basing our beta 1 using yung F prime C, no? Kapag yung F prime C natin is equal, no? So is equal or less than 28 megapascal. So tandaan natin na if F prime C of the concrete is equal or less than 28 megapascal, your beta 1 is 0.85. So ganun kadali yung pagkuha natin ng beta 1. Now, if your FC prime, F prime C, I'm sorry, is greater than 28 and it is equal or less than 56 megapascal, you solve your beta 1 using this formula. So itong formulang to in SI or metric system na, no? Meron kasing equivalent na English. So hindi ganito, ha? So this is for SI units, ha? Now if our F prime C is greater than 56 siguro doon, no? 56. So i-verify ko to, no? I-verify ko tong mabuti, no? Kung 56 or 58. If it is greater than, your beta 1 must be equal to 0.65. Okay? So, ibig sabihin, hindi bababa ng 0.65 yung beta 1 natin. Ha? So, tandaan natin yun. So, nakalimit yung beta 1 natin up to 0.65. Your beta 1 must not be less than 0.65. Ha? Okay? So, that is the how we get beta 1. Ha? Okay, so those are the what? So that is the design assumption number 6, ha? Pagdating natin sa ating concrete, no? Saan na tayo? Okay, so let's move on now to the application of equilibrium and compatibility of strain. Okay, so we're going to use here equilibrium and compatibility of strain. Okay, so we're going to use this one, itong strain diagram, and also we're going to use the stress diagram, no, in our beam. So ang stress natin sa concrete, we're going to use the rectangular, no, rectangular block, the equivalent rectangular block. By the way, the equivalent rectangular block, this is what accepted by the code, no? Okay, accepted by the code because of in agreement with test, no, yung result ng test. So in agreement siya, kaya at naging mas madali yung computation, no? So dito pa lang nakita nyo, meron na tayong mga assumption. Kaya sabi nga doon sa introduction natin, bakit yung nominal strength natin is less than the ultimate, which is the test, because of we are following codes, no? Okay, pina-follow natin yung codes, no? Yung pagkuha pa lang ng beta, this is already what? Written in the code, no? Okay? So now, for the equilibrium, ito yung gagamitin natin sa equilibrium, no? Wherein, since we are considering the rectangular block, so the equivalent compressive force now can be computed using this equation, no? Okay, ano yung equation natin? The compressive force is equal to 0.85 F prime C BA, no? Yung B is the width of the section, A is the depth of the compressive stress, 0.85 is the width of this, or the intensity of this stress, no, the maximum intensity. So that is how we get our compressive force, and the location of this is located at the center of this stress, no, diagram, which is A over 2 at the top of the beam, no? So yun yung ating compressive force. Now, reinforcement, the tensile force is equal to AS Fy if our strain in our steel is greater than or equal to epsilon y. Pero kapag less than, Fs yun. No? So nagkataon dito sa diagram natin, pinakita dito na merong condition that why is it Fy yun? Kasi yung epsilon S natin is greater than Fy, epsilon y. So therefore, if the strain in the steel is greater than the yield strain, your stress in the steel will be equal to Fy, no? So yun ang tandaan natin, okay? Pero kapag yung epsilon S mo is less than the epsilon y, that will be Fs. Okay? So yun ang mga dapat nating tandaan, ha? Okay, so ito yung ating and also here dito sa ating strain diagram, yung ating usable strain in the concrete is 0.003. So yun yung ating strain. Okay, so applying equilibrium, so using the forces, no? So the compressive force is equal to the tension force, no? Ayan. Now for the okay, so when we equate now our T in terms of AS and the stress, okay, ito yung mga condition, no, na binigay pa kanina. Kapag daw yung epsilon S natin is equal or greater than epsilon Y, your epsilon S will be equal to Fy over ES. So automatic yan, or Fs is equal to Fy. Okay? So yun yung mga dapat natin consider. Okay, so ito ngayon yung ating application ng compatibility, no? Okay? So using compatibility of strain, so we have now here our strain diagram. So maximum strain in the concrete, then the strain in the steel. So yung strain natin sa steel, hindi binabanggit dito na more than or equal, no? So generally it is epsilon C. Okay, so by ratio and proportion, no? So by ratio and proportion, we have this epsilon S, no? Relating it to epsilon U. Okay? Remember, epsilon U is, or epsilon C. Other ang mga designation natin dito, epsilon C or epsilon U, no? Basically, it is maximum. It is equal to 0.003. 003 yan. No? So, ibig sabihin ngayon, paano natin na-format to? Okay? By ratio and proportion, epsilon S over D minus C equal to epsilon U over C. Okay? So, pag in-isolate mo yung epsilon S, it is equal to what? 0.003, no? Multiply by D minus C over C. So, yun yung pinagmulan nito, no? Ngayon, kapag kinumpute natin yung Fs natin, no? At sinubstitute natin yung value ng epsilon S here, okay, the result will be what? The result will be this one. And remember that the modulus of elasticity of the steel, yung ES, ang ES natin is 200,000 megapascal. Yung 200,000 megapascal, pag minultiply mo ng 0.003, ang result niya ay 600. Kaya yung Fs natin ngayon ay 600 multiplied by D minus C over C. So ito yung equivalent ng Fs natin, no? Saan mo gagamitin ito? Gagamitin mo ito kapag hindi nag-yield ang steel mo. Hindi nag-yield yung steel. Okay, kasi pag nag-yield ang steel mo, Fy automatic yung Fs mo. Kaya itong formula ng Fs na to, gagamitin mo to kapag hindi nag-yield, no? Okay? Okay? Now, sabi dito, if the steel has yielded, meaning your Fs is either equal or greater than Fy, so ang conclusion mo ngayon, your Fs will be equated to Fy. Then your epsilon S, okay, is equal to Fy over Es, no? Yun ang computation mo ng epsilon S, okay? And then in the computation of your T now will be equal to As multiplied by Fy. So yun yung ating about this first condition. Now, if your steel does not yield, okay, kagaya ng binabanggit ko sa inyo kanina, ibig sabihin yung Fs mo is less than Fy, or your epsilon S is less than epsilon Y. So therefore, T mo ngayon is equal to this, ASFS, or the value of Fs. Ayun. So yun yung magiging computation natin, no? Okay. So ito ngayon, no? In the determination now of the nominal strength. So paano natin kinukompute yung nominal strength? Magmo-moment lang tayo dito. Ito yung mga diagram natin, no? Diagram, strain, stress, then location of our forces. Now, in the determination of the nominal strength, if you are using T, no? If you're going to determine it using yung tensile force reinforcement, ito yung titignan mo. Yung T force mo dito, i-moment mo with respect to C. At ang moment arm mo ay D minus A over 2. Okay, ayan. So, pag hindi nag-yield, ito ang magiging equation mo. Solve mo yung Fs, no? Now, kapag naman ginamit mo yung compressive force in concrete, yung C mo dito, siya naman ang magmo-moment with respect to T. Ito naman yung equation natin. Okay? So, yun yung mga equation natin in determining nominal strength. Okay? By the way, no, what I'm presenting now is actually what? Singly reinforced, no? Singly reinforced lang. Ang kinukonsider lang natin is yung reinforcement sa steel. Okay, so the only what we call it, reinforcement we are considering here is the reinforcement in the tension or the tensile reinforcement. Okay, next. Okay. So, okay, meron tayong tinatawag dito na balance condition. Okay, class. Okay, class. Okay, so medyo mahaba na yung na-cover natin. So we are already okay, so we are already okay, so umabot na tayo ng 1.5 oras, no? Okay, siguro mag-break tayo, no? Break muna tayo. Okay, break tayo ng 15 minutes. Okay? So, break ng 15 minutes. Balik kayo ng 2:60, ano yun? 2:17. Okay? So, break muna tayo. Then, 2:17, tayo bumalik. Okay? So, para makapag-ano rin kayo, no? Okay, so, see you mamaya.
Yes, sir.
Naririnig nyo na ba ako?
Yes, sir.
Okay. Okay, so we have here what we call a balance condition, no? In the in terms of the stress, in terms of the stresses in our concrete and in our steel, no? Okay, so this particular condition, no, in our material, no, exists when the maximum strain at the extreme compression fiber, no? Okay, so yung dalawang uh, strain, no, do sa ating material, sa concrete we have the maximum strain equivalent to 0.003, no? And then for our steel, the maximum strain, no, allowed do sa ating steel is yung yield strain. Okay, yung yield strain. If these two are simultaneously occur on a particular beam, no, on a certain condition, we can say that we have a balanced condition. Okay, so simultaneously mag-a-occur ang dalawang to, no? So aabutan ng concrete yung maximum strain of 0.003 at yung bakal natin mag-yield. Okay? So ang condition kasi kapag na-reach ng concrete yung ating allowed o yung tinatawag nating usable strain, which is equal to 0.003, ibig sabihin magka-crash na yung konkreto natin, no? At balance condition, ibig sabihin mag-yield yung ating bakal. Pag nag-yield ka natin, yun yung pinakasagad, no, do sa ating bakal, di ba? Pag nag-yield yan, it will have a permanent deformation. So pag nasa balance condition yung beam natin, simultaneously magka-crash yung concrete natin at mag-yield yung steel natin. Yun ang balance condition. At ayaw nating mangyari yon, no? Ayaw nating mangyari yon, no? Dahil hindi maganda sa beam natin yun, no? Na magka-crash yung concrete, simultaneously mag-yield yung bakal. But there's a condition in our beam, no, na ganito, okay? Wherein the computation, okay, we have this one, no? Ito yung pinaka-designation natin, wherein yung depth ng rectangular compressive block natin designated as A sub B. At balance condition, the location of the neutral axis is designated as C sub B. So therefore, yung ating compressive force, no, at balance condition is computed using this formula, 0.85 F prime C B multiplied by A sub B, no? And then our tensile force will be equal to AS multiplied by Fy. Bakit Fy? Because mag-yield na yung bakal natin dito, no? So mag-yield na. Okay? So at balance condition, no? So ito yung pinaka-diagram natin. The determination of the C balance, so by ratio and proportion, considering the strain diagram, so C balance over epsilon Cu. Epsilon Cu is equal to 0.003, no, at balance condition. It is equal to D over the sum of epsilon Cu plus epsilon Y. So ito yun. Magdodraw ka ng triangle dito, no? Wala. Meron ba akong line dito? Tingnan ko kung makakapag-draw ako ng line. Ayan. Draw ka ng line dito. Then also we have So, yung triangle doon. Okay, itong triangle dito, tsaka yung malaking triangle na yun. No? So, ito yung relationship ng C balance at ng ating mga strain. So, therefore, C balance is equal to epsilon Cu over epsilon Cu plus epsilon Y multiplied by D. Okay. Okay, so using equilibrium condition, the T balance is equal to C balance. No? Substituting now the values. So remember that A balance equal to beta 1 C balance. No? So ganun siya. So ngayon, if we will substitute C balance equal to kung ano yung na-compute natin dito, pasok natin ngayon dito sa equation. Okay. And then, okay, so yung ating AS balance, no? Using the still ratio raw. Yung still ratio raw, no? Yung still ratio raw is equal to AS over BD. AS referring to the area of the steel, then over B, the base of the section, and D is the effective depth. Kung ano yung computation natin ng D do sa ating previous lesson, yung WSD, ito rin yon, pareho lang, no? So effective depth. Okay, so if we will equate it, no? If we will make use of this still ratio, equating it to balance condition, itong equivalent ng AS balance, which is this equation, substitute natin dito sa numerator, we will have this resulting equation once we substitute C balance. And rearranging this, we have this resulting raw balance, 0.85 beta 1 F prime C over Fy multiplied by epsilon Cu all over epsilon Cu plus epsilon Y. Now, if we will substitute the value of epsilon Cu equal to 0.003 and equating epsilon Y in terms of Fy over Es. By the way, pag i-correct yung copy nyo, this must be beta 1, no? Itong beta dito, it should be beta 1. Now, if we will substitute ES equal to 200,000 megapascal. Okay, so simplifying this quantity in the parentheses, we will have this resulting equation for our raw balance. So raw balance is equal to 0.85 multiplied by beta 1 multiplied by F prime C multiplied by the quantity 600 over Fy multiplied by the quantity Fy plus 600. So this is the formula that we're going to use in determining still ratio at balance condition. No? Pinaka-formula. Okay? So very useful to kapag we're dealing with balance condition. So ito yung required still ratio. No? Para masabi mong at balance condition yung beam. Okay? If it is at balance condition. Okay. We have now here yung computation ng ating reduction factor. I hope you still recall yung intro, yung first lesson natin wherein we discuss, no, about reduction factor pagdating sa strength design. Okay, in the new code, no, kailan ba nag-start ang bagong code? I think yung ACI 2002. The last code no, na na kinonsider pa yung old is yung 1999. Yung 1999 code is still under the old code. So binago nila yung code ngayon pagdating to sa 2002. Yung 2002 version ng ACI code. They call now that code as a Unified Design Provision Code. Bakit? No? Kasi dito ngayon, ina-identify na natin yung mga section natin, mapa compression, mapa tension or flexure member, no? Mapa compression member, mapa flexural member, no? Unified na yung kanilang pag-determine ng strength, no? And that is specifically for the reduction factor, no? Ito yung ito yung basis ngayon for the determination of the reduction factor, no? So we need to identify kung yung member natin ay tension controlled section, kung nasa transition zone yan or nasa transition region, or if our member is a compression controlled section. In for flexure member, for flexural member like this, we prefer na tension controlled yung section natin. We prefer it na tension controlled kasi yung member natin is said to be ductile. No? Ductile yung section, no? Kapag tension controlled yan. Ngayon kapag column naman, we prefer it na compression controlled yung column natin dahil dun malakas yung column. Okay? So we prefer that, no? So ganon. But then again, merong mga section na nasa transition zone, no? So ito yung pagkuha natin ng strength reduction factor. Ito yung value ng reduction factor. Dito naman sa horizontal, dinidetermine natin yung epsilon t. So this is referring to the strain in the tension reinforcement. To be specific, ito yung strain dun sa outermost, or we can say farther layer of bar from the extreme compression fiber. So yung pinakamalayong layer ng bar dun sa ating extreme compression fiber. So usually ito yung unang layer ng bar dito sa ating tension side o dito sa ating tensile reinforcement. Ito yung kinukuha natin, epsilon t, no? So yung epsilon s dito, it referred to the stress for the group of bar, para dito sa group of bar, no? Epsilon s. Itong epsilon t referring to the farther layer of bar from the extreme compression fiber. Okay? So yun yung epsilon t. So mamaya makikita natin yung equation on how to solve epsilon t. Okay, so if epsilon t is equal or greater than 0.005, ang section natin ay tension control, and it has a strength reduction factor equal to 0.90. If our epsilon t is greater than 0.002 and less than 0.005, our section is within the transition zone. So merong equation on how to solve for the equivalent reduction factor. So ang equivalent reduction factor dito, ang value niya nagre-range yan ng between 0.65 to 0.90 if it is what? if we are talking of if we're talking of rectangular or square section, ito stirrup type, no? Pero kapag circular yung ating section, kapag nasa transition zone siya, nagre-range yan between 0.75 to 0.90. So nasa within this range, no? So meron tayong equation para dito. I think yung susunod na slide, no? Yun makikita natin. Ngayon, kapag yung epsilon t natin is equal or less than 0.002, nasa compression control. Our section is considered as compression control. Ngayon, ang value ng strength reduction factor for beam having a stirrup 0.65, whereas for spiral it will be 0.75. Okay, so ganun yung unified design provision. Doon sa old code, makikita mo kapag flexure member yan sa beam, I think 0.90 nakafix yan. It doesn't matter kung ano yan, no? Wala kasing compression control at transition doon. Basta specifically if it is a flexure member like beam, 0.90 kaagad. Kapag naman compression member yan, automatic no? I think 0.70, no, for columns. So iba yung value ng reduction. But for the unified design provision, ito na ngayon ang pina-follow. Okay, so magbuhat 2002 hanggang latest, ito na yung inadapt na code in determining for the reduction factor. Okay, so yun yung about this. Now for the okay, so ito yung ating pwedeng maging ito yung magiging behavior ng neutral axis kapag tension at compression control, no? Kapag tension control yung member natin, what we notice here is that less concrete, no? Kaya gusto nating no? Gusto nating yung beam natin tension control, no? Mas ductile siya, no? So mas ductile yung ating beam, no? So because if you look at here, yung ating yung depth ng neutral axis natin mababaw, no? Ibig sabihin less compressive strength, less concrete ang kailangan mo, no? Okay, kapag tension controlled ka. Whereas kapag compression controlled ka, look at here, yung ating neutral axis mas malalim. Okay? Mas malalim, so mas maraming concrete ang kailangan. So ngayon, ano yung comparison sa dalawang to in terms of the reinforcement? So remember, yung analysis natin pag nag-analyze tayo ng beam, we are using equilibrium condition, no? We are using equilibrium condition. Anong ibig sabihin nun? Yung compression force mo at saka yung tension force mo equal. So ibig sabihin kapag tension controlled ka, no, pag maliit yung C mo, ibig sabihin konti lang yung compression force mo. Pag maliit ang compression force mo, maliit din yung bakal mo. So pag konti yung bakal mo, ibig sabihin yung beam mo, it behave, no, ductile, no? Okay, so yung binabanggit kong ductile, I hope may idea kayo kapag ductile yung beam, no? Kapag ductile yung beam natin, ang ibig niya sabihin, bago mag-fail yan, magdi-deform muna ng todo. Hindi ka agad mapuputol. Dahil, no, Yun, no? Dahil your beam behave ductile. So, ganun yung ating, ibig sabihin sabay na nagwo-work, no? Okay? So, yield muna yung bakal bago magka-crush yung concrete. That's the meaning of a tension controlled section. The reinforcement will yield first before crushing of the concrete. Okay, before mag-crush yung concrete natin. Kaya in actual, mabibigyan ka ng warning. No? Mabibigyan ka ng warning na yung beam mo nagdi-deflect pero hindi yan napuputol. Hindi yan nagfe-fail. So, mabibigyan mo ng remedy. No? So, that is about a tension control section. So, mas ductile yung ano mo. Now, kapag naman compression control yung beam mo, look at here. No? Malalim yung neutral axis mo. Ibig sabihin, pag malalim yan, malaki yung compression force mo. Pag malaki yan, to balance it, dadamihan mo ng bakal. Pag marami yung bakal mo, ang tendency, brittle. Brittle yung beam mo. Ano yung brittle? Ibig sabihin, bago mag-yield yung bakal mo, malulusaw na, magka-crush na yung concrete mo. Pag nag-crush na yung concrete, wala na ngayong mag-hold or magre-resist sa compression. So, mag-isa na lang yung bakal. Pag mag-isa na yung bakal, imagine, ang bakal mo parang mga alambre na lang, no? So, ano mangyayari sa kanya? I-resist niya lahat ng load. Putol kagad siya. Kaya, brittle yung failure mo, no? So, iniiwasan natin to sa beam na mag-design ka ng compression control, no? Na beam. So, usually, gusto natin tension control or we can say ductile, no? Yung, kaya lang meron tayong mga limit dito. Tandaan natin, no? We do not want yung section natin na sobrang liit ng mga bakal, no? Kaya yung kasabihan na sasabihin sa iyo na matibay yan, maraming bakal. Actually, delikado pag sobrang bakal, no? Yan ang tandaan nyo sa reinforced concrete, delikado yan. Kaya wag mo sabihin na dadamihan ko ang bakal, safe ako, no? Hindi. Pag ang nangyari dyan, nag-crush na yung concrete mo, mag-isa na lang yung bakal, yun, no? Ang bakal mo parang alambre na lang, no? Kaya makikita mo, no, bakit may mga nagko-collapse, no? Dami naman yung bakal, meron naman siyang bakal kanila. Because of that, no? Kailangan kasi nagbo-work sabay yan, concrete and tension, no? Yung bakal mo. So they are working, no, simultaneously. Okay, so that is about this, no, about this diagram. Okay, para at least makita nyo pag nagko-compute ka, how do they differ in terms of this the determination of the depth of the neutral axis. Okay, okay, so the wala yung may formula. Ito, no? Ito yung formula actually, no? Na binabanggit ko sa inyo kanina. Para sa stirrups or tie, ito yung formula sa pag-determine ng strength reduction factor kapag nasa transition region yung ating section. Kapag naman spiral, ito naman yung formula, no? So this formula is good for metric, no? Okay, so ito yung formula natin. Okay. So pag spiral naman, yun yung formula, ha? So yun naman ang formula natin. So ito yung eksaktong value kapag tension controlled tayo. Okay, 0.90 yan. Kapag compression controlled, kapag with spiral, 0.75. Kapag others, no, 0.65. Okay, ngayon other actions, kapag shear and torsion, 0.75, bearing on concrete, 0.65, strut and tie model, 0.75. Okay, so these are additional reduction factors given in the code. Okay? So yung kapag transition yung section natin, nasa transition range, ito yung formula natin. No? Okay, so we have here the old code. No? How do we set yung limit sa ating reinforcement? Okay, in the old code, we have what we call maximum ratio, still ratio. Ito, maximum still ratio is computed using this formula. So raw max is equal to 0.75 raw B. And raw balance, yung na-compute natin kanina o yung dinerive natin kanina. So this is the maximum still ratio recommended by the code. No, that is in the old code. Ngayon, bakit nila sinet ito? Ang reason dito para hindi mag-umpugan yung mga bakal, kasi kapag hindi ka nag-set ng limit, yung mga bakal mo magkakadikit-dikit. Okay? So remember, meron tayong required spacing for our reinforcement, no? Meron tayong required spacing. So kailangan sundan natin 'yun. So the determination of the okay, so ito, no? So ito yung raw max natin. Now, kailangan hindi ka lalagpas dito para masabi mong ductile, no? Ductile yung design mo. It should be what? Less than raw max, no? Okay? Yun yung about the old code, no? Yung old code. Okay. The new code, no? That is from 2002 to 2014. So far, kaya nung ginawa ko to, I only have yung 2014 ACI, no? Okay, so the determination of the ductility of the beam, no? We compare our epsilon t to 0.004. If epsilon t is equal or greater than 0.004, your section is said to be ductile. Okay? Okay, ductile yung ano mo. No? So this is the criteria, no? So wala nang raw max pagdating sa new code, no? Actually, merong formula na nakita ko na libro, sinet niya yung raw max, no? But you cannot see that in the what you call it? You cannot see that in the code. Ang nakalagay sa code is actually this one. Ngayon, pag ito kinonvert mo to sa kinonvert mo to sa raw, sa still ratio, you can actually establish yung tinatawag nating maximum raw for you to say na ductile yung beam mo, no? Okay? So I think if you have the book of kung di ako nagkakamali, yung kay Nilsson, no? Nilsson derive. Si Nilsson dinerive niya in terms of raw, no? In terms of still ratio, yung maximum raw for the new code, no? Using this 0.004, no? Okay, in the old and in the new code, meron tayong minimum. Ito yung minimum reinforcement ratio. We have raw min equal to this quantity and also this one. Okay, raw min must be what? Must be the raw min must be equal whoever is greater of the two. Okay, so that's about raw minimum. So whichever is greater of these two will be your raw minimum. Okay? So yun yung about raw minimum. Ngayon, pag kukunin mo na yung steel ratio ng beam mo, all you need is multiply raw min by BWT. BW is the width and D is the effective depth, no? So similarly, ganun din ito kanina. Ito, pag kukunin mo yung maximum steel ratio using raw max, all you need is multiply raw max by B multiplied by D. Okay, so this formula is only good for rectangular or square. Kasi you have your BD. Pero kung triangular, iba yung BD natin. Ano pa ba? I think that's end my presentation. Okay, with regards to the introduction of flexural analysis of beams using strength design. Using strength design. Okay, so I hope may natutunan kayo. I'm hoping na may napulot kayo about the strength design method. Okay, now yung mga pinresent ko sa inyong mga equation, we're going to use those equation pagdating natin doon sa mga problem, no? So ngayon ang gagawin natin, try to read yung mga pinos kong mga problem, no? So read them, no? And then on Tuesday next week, I'm going to present those problems, no? So isa-isahin natin. That will be for next week. Okay? So yung time nyo dun sa lab, gamitin nyo, no? Try to read yung mga given example problem. Okay? And try to look at yung mga books, yung mga book na available, yung kay Nilsson, yung kay McCormack, no? Ano ba yung isa kasi, yung kay McGregor, no? Nakalimutan kong i-mention yung isang libro na ginagamit ko rin, yung kay McGregor, no? So yung tatlong libro na yan magaganda, no? Okay? Yung kay Salmon, maganda rin yun, no? Kung meron kayo nun, mas maganda, no? Kung sakaling makapag-download kayo nung kay Salmon, yung kay Choki, yung kay Wang and Salmon, please try to share it dito sa MS Team, dito sa team natin, para magkaroon yung copy yung iba. Paki-post na lang kung meron kayong mada-download na copy nun, yung kay Wang and Salmon. So para at least may magamit yung mga kaklase natin, no? Okay? And also the other books, no, na binabanggit ko, yung kay Nilsson, yung kay McCormack, yung kay McGregor, no? So kung makapag-download kayo nun, try to paki-post na lang dito sa team natin para yung mga iba nyong classmate magkaroon ng copy. And then try to read, no? Try to read kasi may mga bagay akong hindi na-mention dito sa presentation natin na mababasa nyo doon. At makaka-encounter kayo ng mga situation, no? Na hindi ko mapipresent. Okay? So, yun ang gawin natin. Okay? So, this do sa lab time natin, dahil hindi na muna tayo magla-lab ngayon dahil kailangan ko munang tapusin, no?